Okay, we will get started now. Chapter 2 is only marginally about graphing, but it is all about linear equations, but it's about groups of linear equations called a system of linear equations, and how you solve systems of linear equations using what's called the echelon method. And it's also referred to as the Gauss-Jordan method. There's a whole area of algebra that studies the solution of systems of equations called linear algebra. So we're going to start off with an applications problem. Now this may not be an application that's near and dear to your heart, but agricultural science and business is a big deal these days. This is a very, very simplified problem. It's simplified in that when you are in the farming business and you have to feed animals that you're raising as livestock, you have to make sure that they have all the nutrients they need in their food. And this is simplified because the only two products that we're using to make up this feed are corn and soybeans, and the only two nutrients that we're looking at here is going to be protein and fiber. Now, if this was a real situation, you would be looking at protein and fiber and fat and various vitamins and minerals as well. And there are linear equations that incorporate all those variables, but we want to narrow it down to two because up to this point, the only kind of equations you've ever seen that are linear equations with just two variables. And we'll expand on that a little bit in the next section. So suppose an animal feed is made from two ingredients, corn and soybeans. And one serving of each ingredient provides a specific number of grams of protein and fiber, and that's shown in this chart. So what the chart tells us is that one serving of corn provides 3 grams of protein and 11 grams of fiber. And one serving of soybeans provides 10 grams of protein, which is, of course, lots more than the corn, but only 4 grams of fiber. And since, say we were feeding cows, they need protein to produce milk. They also need fiber to keep everything moving through their digestive system. So let's suppose that we need to know how many servings of corn and soybeans should be used to make a feed for these cows that contains 115 grams of protein and 95 grams of fiber. That's our goal. We want to mix up a feed that makes that. And we're only going to use corn and soybeans. Well, since we don't know how much corn and we don't know how much soybeans, those are going to be our two unknowns, our two variables for our linear equation. And since each serving of corn provides 3 grams of protein, then we would say that the amount of protein provided by X servings of corn would be 3 times X. And then if you talk about the amount of protein provided by Y servings of soybeans, well then, since it's 10 grams per serving, then it will be 10 times Y. And we need that to total up to 115 grams. The food also has to supply 95 grams of fiber. And since corn supplies 11 grams of fiber per serving, and soybeans provide 4 grams per serving, then the amount of fiber equation that we're going to have is going to be 11x plus 4y equals 95. 11 servings of corn plus 4 servings of soybeans needs to total up to that 95 grams that we're required to have of fiber. Now at this point we have something called a system of linear equations. So So I'm going to write down what that system is. So here's our table, and from the table we have figured out that we need, since corn is X, soybeans is Y, and we need a total of 115 grams of protein, and we need a total of 95 grams of fiber. This is going to be our system of equations. Now, there is a method in algebra that says certain things are legal for you to do. Are you allowed to add the same thing to both sides of an equation? Is that legal in algebra? Is that something you do to solve an equation? Yeah, add or subtract something from both sides. Can you multiply both sides of an equation by a number and still have a true equation? Yeah, as long as I multiply both sides. So what I want to do is we're going to kind of play a little game that I kind of call kill the variable. People usually like that game because they don't like algebra. My daughter said years ago when she was first learning algebra, she said, "Mom, why did they have to go mix up the alphabet with math? That just makes no sense to me. Math is numbers, it's not letters." So, you know, I understand that's how a lot of people feel. So kill the variable was a game she enjoyed when I taught her how to do this. So what we want to do is we want to take this system of equations and what I would like to do is I would like to multiply both of those equations all the way across both sides by some number that would allow me to get rid of the x variables in one of those equations. Or both, that would be fine too. Okay? So what I'm going to do first is I'm going to multiply the top equation by 11. But then I'm also going to multiply the bottom equation by the opposite of 3. Now, it's important to see where those two numbers came from. What I did was I took the coefficient of x in the second one and multiplied it through the first one. And then I took the coefficient of x in the first one and multiplied through the second one. And then in order to make the disappearing act happen, then what I want to do is change the sign of one or the other. It didn't have to be the 3 that I made negative. But I need to make one of those two multipliers negative so the cancellation is going to work out. So this is how I'm going to wind up. I now have 11 times 3 is 33x plus 11 times 10 is 110y equals 11 times 115. If you're ever multiplying something by 11, this is actually a neat little trick up here that you can do to figure out what that is, or you use your calculator. But that's 1265. And then I'm going to go through with the second equation. And negative 3 times 11 is negative 33x. Plus negative 3 times 4 is negative 12y equals, and negative 3 times 95 is negative 285. And you can double check that arithmetic on your calculator. So this is the same thing we've always done in algebra before. You can multiply all the way through an equation by a number and it doesn't change the equation. It doesn't change whether or not it's true. So what I have now is I now have a new equation if I can add these two together, which basically I'm adding the same thing to both sides. I'm adding this to this side and this to this side, but this says these two are equal to each other. So if I add these together, notice what happens to the x's. They're dead. They're gone. And then 1y minus 12y gives us 98y. And 1265 minus 285 gives us 980. Okay? Now we're going to take this equation and we're going to replace the second equation with this, because these are all equations, they're all equal. So we're going to take that 98y equals 980, and we're going to add it to, not the transformed equation, but the original equation, 3x plus 10y equals 115. So this system has the same solution as this system. That's the only thing you need to keep in mind, is that these two systems have the same solution. So there's our new system.
You can choose either equation in that situation?
Yes.
Okay.
Yeah, I could have gone back to this one, but because I like a process that's repetitive, I like to always go back to the same thing or use the same position every time, so that I have the same process. Sure.
Hi guys, my name's Liz. I'm from the Learning Center. We're in the bottom floor of the library. We have free drop-in tutoring for math, science, and English classes. So if you ever have a problem, need help, just drop in and let us know what you're working on, and we will let you know who can help you.
Okay, thank you. And they do have a tutor for finite this semester. Normally it's kind of hard to find tutors for finite and calculus, but they do have a good one this semester. So if you need some extra help, take advantage. Okay, so what we've done is we started with this original system. We've multiplied through both equations by a number that lets us kill off the x's. Then we add the remaining part of that equation together to get a new equation that will have the same solution as the original system. So we can substitute this in for either one of those equations. What I did was I chose to substitute it in for the second equation, but I could just as well have taken 11x plus 4y equals 95 and then brought that down as my second equation. So it doesn't matter which one of these you choose to keep. Keep one of the originals and then add your new one as your second equation. So now we've got a system of equations where we have no x's, and we have one equation that actually still has y's, and what we would like to do is we would like to get rid of those y's in the second equation. So what we're going to do on the second equation if you actually look at this one, what you know is that 9y equals 980, or I'm sorry, 98y equals 980. Can't you find out what y is from that one? Yeah. Y equals 980 divided by 98, which is 10. Okay? Now, if you know what the value of y is, could you not find out what the value of x is in the first equation? Yes. This is called back substitution. So we take y equals 10 and we put that in 3x plus 10 times 10 is equal to 115. And of course, 10 times 10 is 100. And if I subtract 100 from both sides, I have that 3x equals 15. And from there, it's pretty easy to see that x is equal to 5. So what that means, then, is that if I make a feed mixture that contains 10 servings of soybeans and 5 servings of corn, that I'll meet both of these requirements up here in my original problem. So in that case, the answer to this question, and again, this is something some of y'all kind of got dinged a few points for on the test, I'm just warning you. The answer to the question is how much each ingredient should be used to meet the dietary requirements. Requirements for 115 grams of fiber and 95 grams of protein, we need 5 servings of corn, and 10 servings of soybeans. When you're asked a question in English, you need to answer it in English, not in x equals 5 and y equals 10. Okay? Your boss is just like you. They don't like algebra either. They don't want to know what x and y are equal to. They want to know what the answer to the question is. Okay? Now, we could have solved that system graphically. And the solution graphically looks like this. And just to show you how you could have done this fairly easily on your calculator, and this is going to be a real shortcut because I'm not going to make you do a lot of algebraic simplification. I'm going to show you how you get your calculator to show you the right graph without having to solve for y the way you normally would and simplify everything. What we're going to do, we're going to get the calculator, turn it on, go to the y equals menu, and I'm going to clear everything off. And remember, we've got 2 systems, or I'm sorry, 2 equations in the system. This one says that 11x plus 4y equals 95, and your calculator wants it to be solved for y. Well, the first thing that you would do if you want to solve it for y is you'd have to move that 11x over to the other side. And then the next thing you would have to do is you would have to divide both sides by 4y. Now that doesn't look like y equals mx plus b. That is not in slope-intercept form. If I convert it into slope-intercept form, that means I have to divide negative 11 by 4 and I have to divide 95 by 4. But my calculator knows how to do arithmetic, so it doesn't need any help from me. What you need to remember, though, here that's going to be the most important is that if you choose to do it this way, there's very little chance you'll make a mistake on the algebra. But you do need to remember that you're going to have to put parentheses around the right-hand side before you do the division on both sides. So we're going to enter parentheses 95 minus 11x, close the parentheses, and then we're dividing both of those terms, which is why we needed the parentheses, by the 4. And then we're going to do the second thing with the other equation. we're going to try to solve this one for y. And when we solve that one for y, what we do is we take that 3x over here with the 115. And then we divide by the 10 that's in front of the y. But again, remember, these parentheses are very important. If you're going to, this is the trade-off. If you want not to have to do the simplifying, you've got to remember the parentheses. Now, before I actually hit graph, are we going to use negative 10 units of corn? No. What's the least amount of corn you can use?
0.
0, none. So we're going to start at 0. Is not the same thing true for soybeans? Can we use less than 0 soybeans? I think so. Now, we actually already know that the answer to the equation is 5, 10. What's going to happen if I graph it right now is I'm going to see the intersection point of these two just barely on the screen. So I'm going to go ahead and hit graph and show you that. So there's your one equation. There's the other one. And you can see the intersection point is way up here at the top, and we really can't go to the right or left of it easily because we can't see both sides of it. And in order to use the calculator to get it to tell us where that intersection is, we need to clearly see the complete cross. So what we're going to do is, do I need to make the screen taller or do I need to make it wider?
Taller.
Taller. How do I make it taller?
Increase the maximum y.
How do I make it? What? Say again?
Increase the y max.
Yes, because taller is y, because y goes up and down. And you need to make the y max bigger. So I'll make it 20. And then we'll hit graph again. And notice that that graph looks a lot more like this graph. And what we're interested in is that intersection point right there. And the calculator can tell us what that is. All we do is hit second, trace, go down to number 5, which is intersect. And it actually goes right straight to the intersection point, but it doesn't always do that. That's just what happens this time because that was basically the center of the screen. So you make sure it says first curve. It doesn't know lines and curves are the same thing. So say yes, this is the first equation, and this is the second equation, and then hit enter and let it guess. So basically you're going to graph the two equations, then second calc, choose number 5, enter, enter, enter. And it tells you that the solution, the intersection point, is at 510. Okay?
So like on the test, we can just do it on the calculator?
Yes.
Okay, sweet.
As long as you show me what you put in for y equals. That's the only restriction I'll make on that. Show me what you put in y equals. Because if you put the wrong thing in y equals and you get the wrong answer, I'll know you knew the process, but you just, you know, it's easy to mess up a sign. Subtract when you should have added, add when you should have subtracted. So yeah, you could do it that way. Now, there's two ways that we've seen this, and this tells us that what we're going to see is that this has a unique solution. Unique means this is the only solution there is that works in both those equations. So that means that's the only answer to the problem there is. That's it, we're done. So let me go back to the PowerPoint for a second. And we solved that problem and we found the values of x and y that satisfy the system of equations is that x is 5 and y is 10. And so now we're ready to look at an overview of what we're doing here. There's actually three things that can happen when you graph those two equations. The first one is what we just now saw. They will intersect at a single point. And the coordinates of that point are the solution to the system. And there's only one point, therefore there's only one solution. But it is also entirely possible, as it says in 2 here, that the graphs are distinct parallel lines. Do parallel lines ever cross? No. Do they ever have an XY pair that is common to both of them? No. So what does that mean about a system where you wind up with parallel lines? Are they ever going to cross? No. So there's no solution, okay? Because they don't cross. That's called an inconsistent system. And then the third thing that can happen is that one of your lines lays right on top of the other line, and every place that the first line is, the second one's there too. They share all their solutions, all their points. And that means then that that's called a dependent system, and it also means that there are solutions, but there are infinitely many solutions. Any point on either line is a solution to both lines. So just so we have a kind of a clear picture of what could happen, in graph A we see a system of equations that has one single unique solution. And it's called a consistent system. Consistent systems have solutions. Inconsistent systems don't have solutions. Graph C is a consistent system. It has solutions. It has infinitely many solutions. Every point that's on A is on B for the two lines A and B. The one in the middle is the one that is parallel lines, and that's the one that is the inconsistent system. It has no solution. So the thing we've seen so far is that we can exchange two equations, we can multiply both sides of an equation as long as we don't multiply by 0, because 0 makes everybody disappear. And we can replace any equation with a non-zero multiple of that equation plus a non-zero multiple of the other equation. In other words, what we did in the last time when we multiplied through by -3 on one and 11 on the other. Okay? So that's the way you do what's called Gauss-Jordan transforming of systems. So this was the system of equations that we've solved. This is the graph that we looked at. Now we're going to look at an example where we have a system that has maybe not a solution. This one has no solution. So here's what's going to happen. We're going to take these two equations, and notice that if I multiplied the top equation by 4, what would happen? I'm sorry, not 4, 2. If I multiply that top equation by 2, what's going to happen?
Variables that cancel out.
That's right, you've got variables that will cancel out. Because 2 times 2 is 4x, and 2 times -3 is -6y, and 2 times 6 is 12. So now if I add these two together,
What's -4x plus 4x?
you just add these two together, what do you get? I get 0 x's, and 6 minus 6, I get 0 y's. But 8 plus 12 is 20. What happens when I multiply x by 0, regardless of what x is? What's x? It killed it.
What about the y's? They disappeared too, right?
So if you got 0 x's and 0 y's on the left-hand side of your equation, you got nothing. But is it true that 0 equals 20? No. That tells you there is no solution. That system of equations has no solution. Now, if you want to know why, what you're going to see happen, and we're going to graph this, prove it to you. We're going to use the same method we did before. I'm going to change our first equation into something I can put in the calculator. Probably not a good place to put that. 2x minus 3y equals 6. I want to set that equal to y, so I need 2x over here with 6. So I subtract it from both sides. And then I need to multiply both sides by divide both sides by -3. So that's going to be y1. And then the other one says -4x minus 6y equals 12. And again, I want that solved for y, so I can put it in y2. So I'm going to move the -4x over to the other side. That gives me 12 plus 4x. And then divide both sides by the -6. And that's what I'm going to put in for my two equations. So y1 says 6 minus 2x divided by 3. And then my second one says 12 plus 4x we're going to divide this one by -6. And I'm going to go just to the graph, and my window didn't show me two equations, but I put two equations in there, right? Okay, maybe it's just the window I chose. So let's go zoom 6, which is your standard window. It goes from -10 to 10 on both x and y. What do you see now? Are those lines ever going to cross? Nope. So are they ever going to have a point in common? No, because they have to cross to have a point in common. So since they're parallel lines, we still have no solution. Okay? They have no points in common. Now we're going to do one that has an infinite number of solutions so you can see what that looks like. So here's our third example. And again, we're going to try to do the kill the variable thing and see what happens. So what can I multiply the first equation through by to get it to cancel out the x's? Yeah, I could do 2. So if I do that, -2 times 3 is 6x. I'm sorry, 2 times 3 is 6x. 2 times -y is -2y. And 2 times 4 is 8. So there's my new equation. But what happens when I add that back together with one of the old equations? Like this one.
Everything cancels.
Everything cancels. Dead x's, dead y's. That means there's nothing left on that side. But what's negative 8 plus 8? 0, so there's nothing left on that side either. Is this true?
Yes.
Yes. That means we have infinite solutions. Okay? And in order to see that, what we're going to do is we're going to graph, starting off with the first one, y equals parentheses 4 minus 3x divided by the coefficient of y is negative 1. And for the second one, we have negative 6x, which when it moves over is going to go with negative 8, but it's going to be added. And then we're going to divide by the 2 that's in front of the y. And let's see if we get what we think we're going to get, which would be only one line. So 4 minus 3x divided by negative 1. And then the second one's going to be negative 8 plus 6y divided by positive 2. And we're just going to hit graph. And there goes the line, and it's still graphing, but I don't see another line. I only see one line. Now, it might be because my window's not set up to where I can see them both. So I could try to zoom out, I could try to adjust the window and find the other line. Here's the easiest way to figure out if it's the same line. Hit your trace button, and notice that it says these points are all on the first equation. So it's tracing on the first equation. If I hit my down arrow key, it moves to the second equation, but it stays on that same line. That second equation has those same points. So that's what tells us there are infinite solutions. It's the same line. There's only one line. That tells you that everything in one line is on top of everything in the other line, and therefore they all share all their points, and it's really the same line. So that's a system of equations that has an infinite number of solutions. Now I'm going to depart from the way that the PowerPoint presents this, because I'd like to go ahead and get us into the next section, because up to this point it's all been graphing calculator and having to multiply and divide, and there's algebra involved. But the truth of the matter is there's a lot more efficient way to do this. So I'm going to go ahead and show you the method we're going to use throughout this whole entire chapter. What we're going to do is we're going to use the Gauss-Jordan method, but we're not going to do all those row operations. What we're going to do is we're going to make a matrix and a matrix has rows and columns. And it's going to represent this system of equations. So what I'm going to do is I'm only going to keep the numbers. The variables x and y always stay right exactly where they are. But I'm only going to keep the numbers.
Is this 2.2?
This is actually an example of 2.1, but I'm going into 2.2 now. Okay? I'm gonna go ahead and show you the method that we would learn in 2.2 so you can see how much faster this is. So a matrix is always enclosed by brackets. And we need 1, 2, 3, 4, 5, 6 entries. So this is called a 2 by 3 matrix. It's always rows by column. Okay? And all we're doing is copying the numerical parts of our system. 3, -4, 1, 5, 2, 19. Okay? This is called the augmented matrix, and where I'm putting this dashed line here is where the equal sign would be. Okay? Now let me tell you what the goal is. The goal is to use those row operations to come up with a matrix that looks like this. It's still 2 by 3 because I'm just transforming those same equations or same sets of numbers. Only what I want to happen is I want my matrix to look like this. And then when I do, that last column of the matrix is going to tell me what X is and what Y is. Without me having to graph, without me having to go through all the multiplying and dividing and adding and subtracting. I'm going to let the calculator do it for me. When I get this, this is what's called the reduced row echelon form. And this is how we're going to get it. So follow along on your calculator. Turn your calculator on. Doesn't matter where it is, what it's doing. Get to the home screen, and if you've got any math on there, clear it off. So that we're all looking at the same thing. Now, how many people have a TI-83 or are using the one on the computer? Okay, all of you can watch what I'm about to do, and the others of you, I'll show you how to get where yours go. On the TI-83, there's a button that says, on the button, Matrix. Okay? It says Matrix. If you have a TI-84, if you have a TI-84, it's not on that same button. On the TI-84, if you look at your X to the -1 key, it says matrix up above it. So in order to access that on your TI-84, you have to press second and then X to the -1. Whereas on the TI-83, you only have one button.
No, you got.
No, it's a shift function above the X -1. It's the same.
On the 83?
Yeah.
Mine's
Yeah.
not. On the 83, it's not this one anymore. Now, yours might be a plus. Some of the pluses.
It is.
Okay, yeah, on some of the pluses, you might have to do a shift function. But I want everybody to be able to get to the screen that I'm going to be on right now. Everybody needs to be to that screen. It doesn't matter if you've got the 2 by or the 3 by or that other stuff on there. That doesn't matter. You need to be on the screen that says names, math, and edit across the top. Okay? This is the names of all the matrices the calculator knows. So it goes A through J. More matrices than you'll ever need to have in this class. If you right arrow, it gives you some math things that you can do with matrices. Most of these you will never use. They use all of these in linear algebra. But we're not going to be engineers, so we're not going to do linear algebra. If you go over one more, it says edit. That's always going to be the first place we're going to go, is we're going to edit the matrix. So we're going to choose matrix A, because it's at the top, and why not? And notice that matrix A is saying it's a 3 by 2. But we need a 2 by 3. A 3 by 2 has 3 rows and 2 columns. We need a 2 by 3, which has 2 rows and 3 columns. Okay? So you have to put in the dimensions of your matrix first. Then you just simply enter the numbers that are in the matrix, which is 3. And you go across the first row and then it'll jump to the second one. So it's 3, -4, 1, 5, 2, 19. You just enter your numbers in your matrix. And then press your second mode key to go back to the home screen. Now this is word of advice. You can skip this step, but you might pay for it later on if you forget it. What I always like to do is I like to actually look at the matrix before I try to do anything else with it, because I want to make sure I entered it right. It'd be really easy not to have done that. So what I do is go back to matrix, and I press enter and ask it to show me matrix A, because I want to make sure that my matrix A matches what I put in the calculator. The next step is going to do everything we've been doing all class period to this problem and tell you what the answer is. Get back to your matrix menu, go over to math, scroll down until you get to option B, which is RREF, that reduced row echelon form. So you hit matrix, go over to math, and go down to option B, reduced row echelon form, and hit enter. Then you need to tell it which matrix you want it to work on. So then you have to go back to your matrix menu again and choose matrix A, because that's the one that we used. And then all you do is hit enter. So there's that same matrix with all the row operations and everything done to it. What's the value of X? 3. What's the value of Y? 2. So the solution to this problem is the ordered pair 3, 2. No extra work. All you have to know how to do is take these numbers, put them in a matrix, enter the matrix in your calculator, and do this. And you have the answer instantly. Okay? That's the method we're going to use all the way through Chapter 2. For all of it.
You can do all of Chapter 2 pretty much on calculator.
We're going to do it all on the calculator. And when you look at this problem, without me going through all of the row operations and all the steps, I will tell you, before we actually solve it here the way I'm going to show you, let me show you on the PowerPoint how many steps solving that problem takes if you don't do that, you don't do matrices. Okay, here's the problem. Oh, and I didn't even leave the steps in there. Ha. Well, what you have to do here first is, and this, we have to do this anyway to be able to do our problem. First thing we're going to have to do that's going to be required anyway is this is not set up in a matrix-friendly form. So the first thing we want to do is we want to get all of these set up to where they're in the form AX plus BY plus CZ equals D, some number. Okay? So that means in this one, I need that Y back over here with its buddies X and Z. So that's what it's going to look like when I move the Y back over here with its friends. And logically, where it needs to go is right there, because it's always X, Y, Z. And then I need to do the same thing with this one. So I need Z over here with its variable friends. The last one is actually already in the proper order. Now, if you did all the row operations to get this problem solved, it takes about 2 pages of all the steps. But what we're going to do is we're going to use the row reduced echelon form, which means we need to start out with a matrix that represents this system. So you need all the coefficients. So fill in any that are missing, because that's the only thing you're going to put in is the coefficients. So that's 1x minus 1y plus 5z equals -6. 3x plus 3y minus 1z equals 10. X plus 3y plus 2z equals 5. So there's your augmented matrix. And your augmented matrix is a 3 for the 3 rows by 1, 2, 3, 4 for the columns. And you need to know that to be able to enter it in your calculator. So again, we're going to go to the matrix. We're going to choose edit. We're going to, and I just keep using matrix A over and over again. I don't use different matrices if I don't have to. So matrix A needs to be a 3 by 4, and its entries are 1, -1, 5, -6, and then 3, 3, -1, 10, and then 1, 3, 2, 5. So enter your values into your matrix. And then once you've got those numbers plugged into your matrix, just quit back to the home screen, clear it, and ask it to show you matrix A, just to be sure that you entered it right. Because if you misenter one of the numbers, what happens when you do your reduced row echelon form?
You're going to get it right.
You're going to get a wrong answer. Okay? So you want to make sure if you put in good numbers, you'll get out a good answer. But if you put in bad numbers, you get out a wrong answer. So we're going to look at the matrix. It's worth the second it takes to check. And it does match. So then we go matrix menu, over to math, down to option B, and tell it it's matrix A. So our reduced row echelon form looks like this. And if I put the variables back in from the equation, these are the x's, these are the y's, this is the z's, and those are the constants. So what this one says is that 1x, no y's and no z's, just 1x is equal to 1. This says no x's and 1 y and no z's, so just 1 y is equal to 2. And no x's and no y's but 1 z is equal to -1. So that tells me my solution is the order triple 1, 2, -1. And since we have 3 variables here, the actual solution to that problem would be a point in a 3-dimensional graph. It would have to have 3 dimensions. You'd have y going up and down, x going right or left, and then z would be an axis going back and forth. So you'd have to actually graph in 2 dimensions to find the graph, which is why we don't want to do that. Okay? But that is the solution to the problem, and you can check that it is. Take those numbers, plug them back into those 3 equations, and you'll see that these 3 values, that ordered triple, solves that system. And that one problem took less time than doing all the rest of the chapter. Even though that one problem would have taken about 15 minutes to do if you did all those raw operations by hand. So
we don't have to do the 1s and 0s for the diagonals and get the zeros in the corner. You just do it on a calculator.
You're going to do it on your calculator. You do not have to do this by yourself. Okay? Because you're doing the same thing if you do it on the calculator, except we're avoiding my ability and your ability to mess up the arithmetic. Okay? Now, how are we going to know if we got one with no solution? How's Gauss-Jordan going to tell us there's no solution? Well, okay, here's our matrix. It is a 2 by 3. Put that in your calculator and tell me what you get for the RREF form. Let's let you do one. So when you do your reduced row echelon form, what do you get?
One negative 2, 0, and 0, 0,
1, negative 2, 0, and then 0, 0, 1?
1. Yes.
Okay. If I put the X's and Y's back in here, can you have no X's and no Y's to be equal to 1? No, because if you multiply X and Y, regardless of what they are, by 0, they both become zeros, right? So what this is actually telling you is that 0 is equal to 1. Is that true? Nope. So when the answer to the question, is that true, is no, then that no, it tells you how many solutions you got. No solution. That is called an inconsistent system. Okay? The matrix tells you the same thing that it would if you went through all the algebra. Let's do this one. I'm going to leave this up to y'all. I want you to write your matrix, do a reduced row echelon form on it, and first person that finds the reduced row echelon form, as you find it, look up. Because I'm going to call on somebody. I'm going to have everybody give me one row. Or not everybody, but I'm going to pick 3 people to give me one row of the RREF form. Shouldn't take you too long. Who's got the first row? Raise your hand if you know what the RF for A is. Got your first row?
I think I do.
Okay.
It's 1,
1,
0. And then it's like 0.142.
You want 7.
And then it's 1.714.
Yeah, there's something a little weird going on here, but everybody's getting ugly decimals, y'all going,
Yeah, I'm getting ugly decimals.
you're getting some ugly decimals. Okay, let me show you a trick. That's why I wanted you to do it for yourself first. Then go back to matrix, clear. Matrix, over to edit, enter. And I have a 3x2 system, or 3x4 system. And it has 1, 2, -1, 3, -1, 1, 6. Whoa. Something did not work right. 1, 2, -1. That should have been 0. 3, -1, 1, 6, -2, -4, 2, and 0. Now, matrix, math. Well, matrix, I should print it out to make sure I did it right. That's why I said to quit. So, matrix A, that's what it looks like. Matrix, math, down to option B. Press enter. And then tell it matrix A is the one we want to do the work with. So is that what y'all saw? If you scroll to the right, you can see the whole big ugly decimal. And they're all long, ugly decimals. Okay? In this particular case, the decimals are not useful. They don't help us. So here's what we do. How many people know how to change a decimal answer into a fraction on your calculator? What do I need to do? That's right. So if I do this, and then before I hit enter again, go to math and choose fraction and hit enter. Now it shows me that those actual numbers for my reduced row echelon form are 1, 0, 1, 7, 12 sevenths. And 0, 1, -4 sevenths, -6 sevenths. But what is that last row telling you? It's all zeros. What does that mean? That means 0x plus 0y plus 0z's, which is a big fat nothing, is equal to 0. Is that true? Yes. Infinite solutions.
How do you find the solution set off that? So that's
Okay.
what's confusing me.
Yeah, because you do actually want to write the solution set. So this is how we do it. What we're going to do is we're going to take this first equation and transform it back. 1x plus 1/7 y, I'm sorry, z, that's z, because 0y. Is equal to 12/7. And the second one gives us no x's plus 1y minus 4/7 z is equal to -6/7. And while you might not like the fact that we've got fractions there, you really don't want those decimals. Notice what do both of these equations have in them? Because this one has no y's and this one has no x's. What do they both have?
7's in the denominator.
They have 7 as a denominator and the variable z. Okay? So z is going to be what we call the independent variable here. We can choose some values for z. Okay? And the way you do this is you take the fact that you have x plus 1/7 z plus 12/7, multiply through by 7. 7x, 7 makes that into 1z, is equal to 12. So that means then that x is equal to 12 minus z and divided by 7. Okay? Then you do the same thing with this one. Y minus 4/7 z. Well, if I multiply through by 7, that's 7y minus 4z is equal to -6. So if I solve this one for y, that's -6 plus 4z divided by -4. And if you want to write it as a fraction, that actually looks better. So x is 12 minus z
Can you scoot your paper over?
over 7. Yes, sorry.
Thank you.
And -6 plus 4z over -4. And then the last one is z. So that's what's called a particular solution. It still has a solution, but the solution depends on what the value of z could be. Okay, now we're going to pick up there next time, and we're going to do an applications problem, so be looking ahead. Maybe take a few notes ahead, because we're going to talk about this convenience store problem next time.